The wonderful world of kinetics. What are kinetics? They are the measure of how quickly chemical reactions proceed via rates. That's one of the operative words from this unit. The variables that affect the rates of reaction and the theoretical mechanisms of reactions. How do the chemicals actually combine? What's the difference between kinetics and thermodynamics? Thermodynamics explain to what extent does a reaction occur. That sort of is like our equilibrium unit. Whereas kinetics explains how fast equilibrium is obtained, right? How quickly does the reaction occur? So understanding kinetics, the first thing we need to do is sort of think fundamentally what's happening here. So if we have a reaction, right, shown here, different chemicals combine to produce different chemicals, and we want to try and think of how quickly do certain chemicals disappear and how quickly do certain chemicals appear. And so for this example, we're just going to focus on the forward direction. We'll add in the little tricky bit of equilibrium later. So as the reaction proceeds, the concentration of W2 and XC4, they are going to decrease because they're reactants. The concentration of the reactants is going to go down. Whereas alternatively, W2X and WZ2, their concentrations you would expect to increase as this reaction proceeds, right? So we start with some amount of, so we'll say this is moles and this is time. We'll say this is reactants, and this is products. Right, so the reactants should decrease, the products should increase. Now, how can we write this out mathematically? I've shown you the first one, that the change in the concentration of species W2, remember that delta means change. When you get to calculus, you'll get a lot more familiar with these deltas, right? For those of you in calculus, think of this as a derivative. These are instantaneous rates of change. For everyone else, just understand that this means the concentration of W2 is changing with respect to a certain amount of time, right? So say every 10 minutes, the concentration of W2 changes by, X amount. Now, where did this 2 come from? The 2 came from the stoichiometry, so you do have to factor that in, right? That always goes in the denominator. Now, I said here that rates cannot be negative. And you're like, but Mr. Hicks, you put a negative sign here. Well, what is the change in W2? W2 is decreasing. So this delta W2 right here is negative. It's a negative number because it's decreasing, right? So this negative and this negative multiply to overall give you a positive number, right? So the reactants will have negative signs in front of them. So this is going to be equal to the rate of disappearance of XZ4 after some amount of time has passed, right? This will also be equal to the rate of appearance of W2X after some time, which will also be equal to the rate of appearance of WZ2 for some time. But be careful, because here we have stoichiometry, so we need to put that stoichiometry in the denominator. So these are considered instantaneous rates. So or maybe these aren't instantaneous rates. Maybe we shouldn't get into that distinction just yet. But basically what this is it describes the relationship between the rates of appearance or disappearance between chemicals in a reaction, okay? More generally in this unit, though, we don't work with these types of rate definitions. We work with rate laws. So after you've integrated them, basically, well, sort of. So if you have a reaction like this, A plus B yields C, you could write out a rate law that looks something like rate equals K times A times B squared, right? So this is obviously the rate. This K here is called the rate constant, right? And its units depend on the concentrations, right? This is A, this is B. All this is showing is that sometimes these concentrations can have exponents on them, right? It's not always going to be 2. This is just a generic example. And so this is a way that we can write out a rate law for a reaction, okay? If you have a equilibrium, for example, right, what's special about equilibrium? We know that equilibrium is when the forward and reverse rates are equal to one another. So we'll give the forward reaction a rate constant of K1, or I guess that's the backwards. So this is the forwards, K1, and the reverse one would be K negative 1, right? So this describes the reverse reaction, so C converting into A and B. This describes the forward. So when is equilibrium met? It's met when the rate for going forward equals the rate for the reverse. So we could sort of write that out as K1 times A times B. And we don't yet know what these exponents are, so we'll just give them variables, would be equal to K minus 1 times C with its variable up there. We'll figure out how to figure out what those variables are later. But this is the definition for equilibrium, right? When the forward rate is equal to the reverse rate. Okay? Most of the time for this class, this is the form you're going to see rates written in. Sometimes you'll have to deal with rates written like this, but we'll deal with that a little later. I don't think these are instantaneous. I'm pretty sure those are average rates. Anyway, we'll deal with that later. Okay, so let's dive into a little bit more on rate laws. So here I've given you a rate law. Rate equals K times the concentration of A squared the concentration of B to the negative 0.5 and the concentration of C to the 0, right? So this is just, we're assuming this is what we have. This is just for a specific reaction, right? So the unit for rate is always molar per second, or molar inverse second, right? That's always what it's going to be. Always. That's the unit for rate. Okay? You can define the order of the example reaction as the sum of all exponents. What are our exponents? 2, negative 0.5, and 0. So this would be 1.5. So the order of this entire reaction would be 1.5, right? That's an important word. Then you can also define the order of the reaction with respect to species. So the order of the reaction with respect to A is 2, because look at the exponent. For B, it's negative 0.5, and for C, it's 0. Why is this important? Because the order tells us how the species affects the rate, right? If you change the concentration, right? For example, if I double the concentration of A, that's going to affect the rate by a factor of 4, right? 2 squared is 4. So if I increase the amount of C, you'll notice that it doesn't have any effect on the rate because all the concentrations of C are raised to the 0 power. So the orders help us understand how the chemicals affect the rate. So the next question is, I just sort of answered it, does the rate of the reaction depend on the concentration of C? No, because it is zero order, right? Changing the concentration of C will never affect the rate because it's always raised to the power of 0. Anything raised to the power of 0, no matter what the number, is going to be 1. So it doesn't matter. Okay? The rate constant, which we know as lowercase k, what are its units? Like we said previously, the units for the rate constant depend on all the concentrations of these things. The way you do this is you set molar per second, which is sort of the rate, equal to K, and then you want to put in the molarity units depending on the exponents. So concentration is always in molarity. So here we have molarity squared, right? That corresponds to the A squared. Then we would multiply that by molarity to the negative 1/2. That corresponds to this, B raised to the negative 0.5. And then finally we have molarity to the 0th power, which corresponds to C. The reason why we're using molarity is because that's what concentrations are measured in, right? A is the molarity of A squared. So simplify this. We have molar, right? This is always what rate is, molar per second. We have K. M squared times m to the negative 1/2 times m to the 0 is m to the 1.5. Then if I isolate K by itself, I get m over second times m to the 1.5. Right, so how do my m's simplify? I end up with m to the negative 1/2 over seconds. So these are the units for my rate constant for this specific example, right? This is always how you're going to set it up. So let's do another example. What is the rate, what are the units for the rate constant for the rate law given here? So again, rate is always molar per second. So you start with molar per second equals, we don't know what the units are for K yet. We're trying to figure out what those units are. Then we have molar cubed, which corresponds to A cubed, and we're multiplying that by molar to the 1st power, which corresponds to this, right? The molarity of B raised to the 1st power. So if we simplify this, we get equals K times molarity to the 4th. So if we isolate K by itself to figure out what its units are, we get divided by m to the 4th. So this further simplifies to be m to the negative 3 times inverse seconds, right? Those are the units for the rate constant for this specific reaction, right? M to the 1st over m to the 4th, 1 minus 4 is negative 3. Okay, so now let's move on to integrated rate laws. So integrated rate laws has to do with graphing. And it also has to do with the way you manipulate your data. So there are 3 of these, and the first one is a 0 order reaction. So a 0 order reaction would be given a rate law that looks like this. So you have rate equals K a to the 0th power, right? That's why it's called a 0 order reaction. So if you integrate this, and you'll learn how to do that in calculus, you would get an equation of the form shown here in black. It's incorrect in your notes. This is called the integrated rate law. This is a 0 order integrated rate law. Hopefully you're noticing that this looks a lot like y equals mx and b. Oh, very nice. So this is time, This is the rate constant. This is the initial concentration of A, right? A naught is initial. And this is the concentration of A at time t. So after some amount of time, what is the concentration of A? So if you were to make a graph of this, right, and you plotted the concentration of A versus time, lowercase t is time, right, you'll get a line, right? And the slope of this line is negative k. Nothing special. Down here we have time. Here we have concentration of A. So basically what this is if you just take the concentration of A and you plot it versus time, if you get a straight line, you can say the reaction is first order, right? What do I mean by that? I mean, if you try and do this for some reactions, right, you get data, you plot your data, right? You plot the concentration of A with respect to time. Sometimes you won't get a straight line. Sometimes you'll plot this data, concentration versus time, and you'll get something that looks, like this. Since it's curved, we know that this is not zero order, right? This way of graphing is a diagnostic tool to see, is the reaction zero order? It is considered zero order reaction if, when you plot concentration versus time, you get a straight line. If you get a straight line, you can say the reaction, sorry, this should say zero. Sorry. If you get a straight line when you plot concentration versus time, you'd say it was zero order. Okay? Now, after zero order comes first order, right? So here we have a first order. We would say that the rate would be equal to K times A raised to the first power, right? Since the whole reaction's first order. The integrated rate law you can write in two ways. You can write it this way, or you could take the natural log of both sides, and I'll do this like this, right? So then we have the natural log of this equals the natural log of this plus the natural log of this, right? Those are our log rules. Then we end up with right, the natural log of e to the something is something. So this is actually the rate law that I want you to focus on. You don't necessarily need to be able to derive that, but that's what I want you to focus on, because hopefully you see this also looks like y equals mx plus b. It's very similar. So if I make a plot of natural log of the concentration of A versus time, not just the concentration, this time the natural log of the concentration, what should this look like? It should again give us a straight line with a slope equal to negative k. So here we've still got time as our x-axis, but now instead of just concentration of A, I have the natural log of the concentration of A, right? So as a similar deal up here, if you have data, if you have some concentrations of A, right, and you take the natural log of them, and then you plot that versus time, and if when you do that, you get a straight line, then you can say that it is a first order reaction. If you have some data, right, some concentrations of A with respect to some times, you do the natural log and you plot it and you don't get a straight line, maybe you get something like this, right? That's not first order, right? It's only first order if when you plot the natural log of A versus time, you get that straight line. Another thing about first order is that all nuclear decay is first order, so it follows these kinetics. The half-life equation for first order, so the time it takes to get to half the concentration is equal to the natural log of 2 over k. This is the time required for half the compound to react. Right? So basically it's like, okay, if I have 10 coppers, after 5 minutes, I have 5 coppers. We could say the half-life would be 5 minutes, right? It took 5 minutes to get half of what we had. You can calculate the half-life for reactions by using this formula here, right? This is the rate constant, that K is the rate constant for the specific reaction. This is definitely something that you need to know because it's a question that pops up a lot. What is the half-life of X reaction in its first order? Okay. What comes after first order but second order? And so the rate law would look like this, right? A second order reaction. So the integrated rate law is shown here as 1 over the concentration of A equals all that stuff. And so now, instead of plotting the natural log of A versus time, we're going to plot 1 over the concentration of T. Because I want you to see, and hopefully you see, that this looks a lot like Y equals mx and B. Again, another straight line variation. So here, if I plot 1 over the concentration of A versus time, I will get a straight line if it's actually second order. And now notice that the slope is equal to positive K, right? These were negative K. This is positive K, okay? What this means, as in the 0 and first order, is that if you have some data, if you have some concentrations of A, and you take all those concentrations and you divide 1 by them, you'll have a new set of data. You'll have 1 over the concentration. If you take that and plot it by time, and you happen to get a straight line, what that implies is that that reaction is second order. You have to check. It might not be second order. You might do that, and it might not be a straight line. Then you know it's not second order. But if you manipulate the concentrations to look like this, if you divide 1 by all of them, and then plot it by time, and you happen to get a straight line, that means it is second order. Okay? So now let's talk about the Arrhenius theory, right? Let's zoom in a little bit and really try and think about what is happening that affects these rates. So we have an equation called the Arrhenius equation. It's the rate constant is equal to A e to the negative EA over RT. K is the rate constant, just like we've seen in all the other rate laws, integrated rate laws and everything. And it depends on a lot of factors, right? It depends on everything over here. So A is generally called the pre-exponential prefactor, or just pre-exponential factor, or just the Arrhenius constant. I like the Arrhenius constant. It itself, that A, right, is actually composed of several things. One of those is the frequency factor, often used Z to describe it, and the orientation factor, used with a lowercase rho. You might see that later on in more advanced chemistry classes. So the frequency factor deals with frequency of collisions, right? For a reaction to occur, you may need a chemical to bump into another chemical, right? They need to collide with one another to maybe form a new bond, to do something interesting. If nothing's colliding with anything, obviously no reactions are happening. If you can somehow get those collisions to increase, you're increasing the chance that a useful chemical reaction occurs, right? The orientation factor has to deals with how the, we'll say, chemicals collide. Only certain orientations lead to reactions, right? So say, for example, let's complicate this picture a little bit and say that if the two red dots hit each other, nothing happens. But if, say, for example, we do this again, and instead the blue dot hits the red dot, right, this might lead to a new compound. So we'll draw a new one like this, right? If this goes nada, nothing happens, right? So here that shows that the molecules need to hit each other in a very specific way, right? That's what the orientation factor means. You don't ever really have to do any math with these. It's just something that you should think about. Okay, so there are other things in the Arrhenius equation. Temperature is for T, obviously, so this is temperature, and it'll be in units of Kelvin. R is going to be the, I'm pretty sure that's called the gas constant, but it's not the gas constant that we used in the gas unit. This one's going to be 8.314 joules per mole Kelvin, right? And the way that I like to remember that it's this one with joules is because EA is called activation energy. The energy helps me remember that I need units for energy, right? And if you think about that other gas constant, liter, atmosphere, mole, Kelvin, there is no energy in that one. So if you're using that one here, then that's not going to work. And activation energy obviously has units of joules. Okay, so the new thing here is the activation energy. What does the activation energy mean in the context of a reaction? So here I'm showing you a diagram that should be very familiar. The activation energy is actually here, right? So it starts from where the reactant starts, and it goes up to that hump. And the activation energy is the energy barrier that impedes the transformation of chemicals into other species, right? So for A and B to combine here in this reaction to form C, they basically need enough energy to get over this hill. If they don't have that much energy, then you'll never produce any of C, right? They have to have at least the same amount of energy as the activation energy to get over that hill, whatever that amount of energy is. If they don't, they will not go. So what is the activation energy? We've shown that. What is delta H of reaction? Delta H of reaction is the difference in energy between the products and reactants. So here's how you would calculate delta H reaction, right? This would be an exothermic reaction, okay? So, because delta H would be the delta H of products minus the delta H of reactants, right? The products is lower in energy than the reactants, so you would get a negative number. How would adding a catalyst affect the rate of the reaction? This is a question that gets asked a lot on the AP exam. Adding a catalyst lowers the activation energy barrier. How would that look different? You would literally just redraw this with a smaller hump. So this is with a catalyst. So see, with a catalyst, it requires less energy to get over that new activation barrier. Without a catalyst, right, it takes a lot more energy to get over that uncatalyzed activation energy barrier, right? So you don't change any other lines, you just literally lower that barrier a little bit if it says about adding a catalyst. Okay, so now we're going to try and figure out how do we actually determine rate laws from experimental data? How do we figure out what those exponents are? Right, this is figure out those exponents. So we can write a general rate law for this reaction. We'll say the rate law for this reaction here would be equal to K times A times B. We do not know what these exponents are. These exponents are not necessarily related to the stoichiometry, right? They're not necessarily 1 just because the stoichiometry is 1. They're not necessarily 2 just because the stoichiometry is 2, right? You can't necessarily just go off of stoichiometry. So how do we do this? So basically, we want to observe how changing concentrations affects the rate. So here we've got the rate, here we have concentrations, right? So first let's work with A. Let's try and figure out what A's exponent is. So we want to find 2 experiments where the concentration of A changes, so we can see how that affects the rate, but everything else remains constant. Everything else, I mean, let's say, but the concentration of B and the concentration of C remain constant. We are just currently focused on how does changing the concentration of A affect the rate. We don't care about B and C. We'll deal with those later. So we don't want them to change. So for this one, we need to look at some reactions. Let's start with reaction 1. Okay, so I'm going to highlight reaction 1. And then let's find another reaction where the concentration of A changes, but everything else remains the same. So here, let's do concentration, we'll do experiment 2. So notice how for A, the concentration decreases, but everything else stays the same. This is the same, this is the same, right? Okay, so you need to then pick an order that you're going. So let's say we go from, let's do 2 to 1, right? Okay, the concentration of A from experiment 2 to 1, how does it change? The concentration of A increases by 10, right? If you multiply 0.01 by 10, you get 0.1. Now compare that to how does the rate change? We went from 30 to 3, so we multiplied by 1/10. It decreased by 1/10. Right? Do you see that? The concentration of A from experiment 2 to 1 increased by 10, whereas the rate, though, decreased by 1/10. So we want to think, how do we make a times 10 equal to a times 1/10, right? This is where we're going to figure out what our exponent is here. Let me erase some of these highlighters. This exponent is the same as this one. So 10 raised to the what gives us 1/10. So that means that x has to be -1. So that is the order with respect to a. And I have written all of this entirely too big, so I'm going to shrink it up a little bit. Okay, so we know now that x is -1, right? Okay, let's look now at B. So we want to find two experiments where the concentration of B changes, but A and C are the same. So let's get rid of all this stuff. Let's do, so you have to look. Oh, I see. So B, okay. So for B, we're going to do experiment 2 and experiment 4. Right, so notice we're going to go from 2 to 4. It doesn't matter which way you go. You can go 4 to 2, 2 to 4, whatever. You don't necessarily even have to pick 2 to 4. But you'll notice that A stays the same, C stays the same, right? Going from 2 to 4, look at how the concentration of B changes. So the concentration of B does what? It doubles, right, by a factor of 2, so times 2. Look at the rate, though. The rate does not change, right? So it would be times a factor of 1. How do you go from 30 to 30? Multiply by 1. So now you want to think, how do I make a times 2, right, which we're going to give y. How do I make a times 2 equal to a times 1? That means that y has to equal 0 because it doesn't affect the rate. Changing the concentration of B obviously didn't change the rate at all. So now we can rewrite this rate law. Rate equals K, A to the -1, B to the 0. Okay, and again, I have made this too big, and I want to talk a little bit more about this. So that's how we experimentally determined what those exponents were. Now what I want us to do is find the units for K for this law, for this rate law. Okay, so remember how we do this. The units for rate are always molar per second. And then we'll put K, because that's what we're solving for. A is raised to the -1, so that's molarity to the -1. B is raised to the power of 0, so that's molarity to the 0. So this simplifies to here. And if I isolate K, if I solve for K, then I end up with molar over this. 1 minus -1 is positive 2. So this ends up being molar squared inverse seconds, right? 1 minus -1 is 2. So here are the units for our rate constant for the specific reaction. Okay, now for the hardest part of kinetics, definitely the hardest part, which is mechanisms. So we're not going to get the full picture on this today. We'll keep talking about this, but this is going to get us started. Each step in a theoretical mechanism is referred to as an elementary reaction, and we'll look at those in just a moment. Mechanisms are basically a series of small reactions that when you add them all together, you get the overall reaction. Okay, here are two important things. A compound that shows up in the mechanism but not in the overall reaction is referred to as an intermediate. A catalyst is added at the beginning of a reaction and appears as a product. You might have heard that in other classes. A catalyst doesn't get used up, and we'll see that later on. One of the most important things about mechanisms is that all the elementary reactions, right, which is the different steps in the mechanism, should always add up to give you the overall reaction. We got a little bit of practice with that when we were dealing with, in the equilibrium unit, we were adding reactions together. Okay, you'll often be told that one of the elementary reactions in the mechanism is the slow step. The slow step in a mechanism, whatever the question tells you, and they often just say, this is the slow step, right? Whatever that reaction is, that is the rate determining step. That slow step, whatever they say, that's the slow one, that determines the rate. It's the rate determining step. RDS. Super important. The stoichiometry of the slow step determines what the rate law is. So whatever the rate law is, it's going to be determined by whatever the question says is the slow step, right? The rate law, whatever you have, rate laws look like this, remember? Whatever rate law you end up writing, it should match whatever the slow step is. Now, the thing here that's tough is that the stoichiometry in elementary reactions does determine the order of chemicals, right? Notice if we zoom back up here, you see that there's a 1 in front of the A and a 1 in front of the B, but you'll notice that those 1s have nothing to do with the order of these chemicals, right? The stoichiometry has nothing to do with it. In elementary reactions, though, the stoichiometry is the same thing as the order, right? So whatever the stoichiometry is, you already know sort of what that rate law is. It's different. They're not the same. This is not an elementary reaction, right? It's not part of a mechanism. So let's look at that. Here we have the formation of CO2 and nitrogen monoxide. You can understand this reaction as the sum of 3 elementary reactions. These are the elementary reactions. And we can test, the first thing you should always test to see if it's a valid mechanism is add those things up, right? So let's add these up and see what happens. I'm going to cross stuff out, but you might not want to. So notice I've got an NO3 on the product side, an NO3 here. I've got an NO2 here, an NO2 here. I've got, let's see. Okay, yeah, this is looking good. So I end up with 2 NO2 plus 2 CO yields 2 NO plus 2 CO2, right? Because there's 2 NOs, 2 CO2s. Now what can I do with all these 2's? I can erase all these 2's, and you'll notice that when I add all the steps of this mechanism together, I get the same thing as the overall reaction. That's always the first step in verifying, that's always the first step in verifying if the mechanism is valid. Add the steps together, right? All elementary reactions should sum to the overall reaction. You have to have that in your memory. All right, so let's keep going. I'm going to erase this because we don't, well, I guess I could leave it. I'll erase these lines though. Okay, so steps 1, 2, and 3, they could either be described as all unimolecular, bimolecular, termolecular. What I mean by that is how many molecules are coming together in that specific step. We've got 2 molecules coming together, 2 molecules coming together, 2 molecules coming together, right? What that means is that, the carbon monoxide and that nitrate have to come together to form the products. So we would say that all of these would be bimolecular, not biomolecular. Bimolecular elementary reactions. You could have like a unimolecular elementary reaction if it just went like that. You could have a termolecular if you had something like this. right? You have three things coming together, termolecular, to form the product, or you have just one thing spontaneously converting into something else. So the question says, if the first step is the slow step, so this is the slow step. You're being told it's the slow step. You often are told. And it has a rate constant of K1. What is the rate law for the overall reaction? Remember, the stoichiometry of the slow step determines the rate law. The stoichiometry of the slow step determines the rate law. So let's look at the stoichiometry of the slow step. It wants us to make a rate law. So we have rate equals K1. And what are the things in step 1, in that slow step, that determines what the rate law of this is? We have NO2. Now you're like, oh gosh, what's the exponent there? Like we said previously, for elementary reactions, the stoichiometry is going to be the order. It makes it a lot simple, but only when you're dealing with elementary reactions in a mechanism. Okay? If step 2 was the fast step and has a forward and reverse rate of Kf and Kr, so we'll say this is the fast step, respectively, how could you express the relationship between the forward and reverse rates? So whenever you have a fast step, the forward rate equals the reverse rate. The reason for that is because since it's moving so fast, since it is the fast step and its rate is faster than the other elementary reactions, right, it can essentially establish equilibrium on its own. And so, yeah. So you would say for this one, since that's the fast step, we would have, so the forward rate would be CO times NO3 times KF for forward equals K reverse times CO2 and NO2. Right, so the forward rate equals the reverse rate. Again, the stoichiometry, because these are elementary reactions, determines the order with respect to these different chemicals. So all these are 1 because all the stoichiometry here is 1. Okay, but the fast step, you can say the forward and reverse rates are equal. Final question, are there intermediates in the mechanism shown above? So an intermediate is something that shows up in the mechanism, right? We'll say after the first reactants react, but not in the overall reaction. So remember, when we were adding these things together, we crossed some stuff out. So we were able to cross the NO3s out, and we were also able to cross the NO2s here. Right? So NO2, though, does show up in our overall reaction. So NO2 is not an intermediate. But notice that NO3 shows up in our reaction, but not in the overall reaction. There's no NO3s here. So NO3 would be considered an intermediate, is considered an intermediate. Okay? And this has been a riveting start to our kinetics unit. This is basically everything. This is the whole unit. And so now we just need to do practice problems so you can sort of get used to how all this stuff is operative. There's one more bit of stuff about mechanisms that we need to learn, but that will be that for kinetics.